Okay, so welcome everybody, and we are very happy to have Professor Saslow today at our colloquium. And Wayne did his undergrad in the University of Pennsylvania, then was a grad student at UC Berkeley and UC Irvine. And since 1971, he works in Texas A&M University, where he's still being a professor. And so what's great about him is that he worked in many areas of condensed matter, and lots of his papers are single author, so he prefers to go deep into stuff, and that's what we will probably hear today. So,
thank you very much, Jaroslav, for hosting me and for bringing me here. I live in a small town, so you may not think of Columbia as a big town, but compared to my town, it's a big town. Okay, so it's kind of nice to see traffic and activity and such. Anyway, it's a pleasure to be here, and so here's the talk. I've probably over-engineered it a little bit. I hope I don't sound like a drone. I myself don't take to being over-engineered, even if by myself, so probably it will seem reasonably spontaneous. At least I hope so. So it's three-velocity theory of supersolid dynamics. I will first talk about superfluid dynamics. Okay, two-velocity superfluid dynamics. It's basically assuming you know zip. Okay, so and then I'll take you through to the very end. And oops, what did I do here? I just killed it. Okay, so if you've got questions, just ask. Okay, right? So here's an outline. I'm going to talk about superfluidity in the boson helium-4. First, the experiments. Well, superfluidity discovered in '38. TISA also had a two-fluid model developed. And then later in '41, Landau developed a microscopic picture and a two-fluid macroscopic theory that is basically the one we accept now. There was superfluidity in the fermion helium-3 discovered in '72, and the accepted microscopic theory came along very quickly. It's based on BCS theory, Bardeen, Cooper, and Streecker theory, which was developed in '56 for superconductivity. In other words, pairing. But at the macroscopic level, the theory is an anisotropic version of Landau's two-fluid macroscopic theory. And there's something in that theory that's called the normal fluid density, also the superfluid density. They're isotropic in the case of the boson helium-4. In the case of the fermion helium-3, they're anisotropic. Okay, so there's a preferred direction, so it's got some anisotropy. Well, I'm then going to talk about superfluidity in atomic gases, and that was actually, I said, okay, it was actually observed first in 1999, and the theory that's used for it typically is Gross-Pedievsky theory, which has been used for the boson superfluidity as well. And the Landau's two-fluid macroscopic theory is also used for this, but it needs more. Okay, when you get to what seems to be a super solid behavior. Okay, and I'll talk about that. By the way, right off the bat, I have to say the way people can tell there's superfluidity in the first case, let me go back, is that they see quantum vortices. That's not the only way, but it's a surefire way of seeing it. And that's what in a supersolid, vortices are also seen. And it's relatively recent, the experiments in the last year or two. There was a two-velocity theory for this kind of system proposed by Andreev and Lifshitz, not for the atomic gases, but for the boson situation. And there was also a microscopic quantum mechanical phase flow theory for the superfluid fraction given by Leggett. And zero temperature, it gives a superfluid fraction, F sub s, that's less than 1. All right? And just a comment now. At zero temperature, there are no excitations, and that means there's no normal fluid, according to Landau. The excitations are totally responsible for the normal fluid. So at zero temperature, you've got no normal fraction, you've got a lacking superfluid fraction, something is missing, okay? And so we argue that the missing mass fraction requires a 3-velocity macroscopic theory, and I'll present it. I'm not going to go through I'll tell you what, the structure is like at the end, but I'm not going to, you're not going to have a lot of, mathematics for that. Yes?
Very quickly, I'm seeing the use of the word two in two different contexts. Two fluid and two velocities. Are they different?
Really, they're the same thing, except when it's a 3-velocity theory, one of them is for a solid. So there's normal fluid, good question, superfluid, and a lattice velocity, which is sort of super, but I don't want to call it that. Okay, I could, but then it gets a little, there's superfluid, supersolid, so I'll call it the lattice velocity. Okay? So let me take you back to the beginning. Actually, it starts earlier than the 30s. There's a history that Balabar wrote, and there's a reference to it. In 24 in Leiden, Onnes and Dana found 2 phases of liquid helium-4. Helium-1 and helium-2 below the temperature T lambda, 2.18 K. And here's a figure that illustrates what's going on at press. Shows you pressure versus temperature, and I should know how to do this, but I don't for the
What
laser.
For the point there,
Yeah.
the red.
Oh,
Yes.
gotcha. Thank you. Okay, good. So you see what's going on here. So at high temperatures, you can cool it down in this region. You're going to get helium in the one phase. And that's just an ordinary fluid. And then you go below that if you're under pressure, and you go into helium-2, or you just stay at low atmospheric pressure, and you just cross it at a lower temperature. And I guess this is the 2.818. I really don't know exactly. It looks like that, but it might be at a different
And you're
temperature.
showing this slide?
Excuse me?
You're showing this slide without knowing it?
Yes, I am. I'm allowed. Most people show a million figures and can't answer a single question about them. But it doesn't really matter. Okay? It has nothing to do with what the talk is
We
really
understand.
about. Okay? So, anyway, in 32 in Toronto, where they could liquefy stuff, McClellan found that liquid helium doesn't bubble below that lambda temperature. And this is an interesting phenomenon. So here's some figures. Above the lambda temperature, you get bubbling, and below it, you get no bubbling. So there's a picture, bubbling, okay? Below it, no bubbling, nice and clear, okay? So some more experiments now. All right, Keesum found that at the transition, the specific heat has a sharp maximum that looks like a lambda, and that's why they call it T lambda. So there's the specific heat data that gives the name to the T lambda. And before that, there was no treatment of that. There was no name that I know of for that temperature. In 37, again in Toronto, the department head, who's the only one on this paper, and an undergraduate named Misner, whose name will show up later, and 2 technicians use an oscillating fiber method to measure the viscosity of the stuff. And he found that there was a decrease in the viscosity in helium-2 as the temperature decreases. Okay, you're losing viscosity somehow. Okay, and from experiments in the range from 35 to 37, experiments in Leiden and Cambridge, it gave anomalously high thermal conductivities in the helium-2 phase, which explains the disappearance of bubbling because below T lambda, because the temperature would be evened out very quickly, and therefore there'd be, it's bubbling. We know you boil water, right? It's hotter on the bottom than on the top. But if the temperature is made uniform, you're going to lose that bubbling. Okay. So in late 37, Kapitsa in Moscow and Allen in Cambridge independently show that the helium-2 phase has an extremely low viscosity, and that means that laminar flow is suppressed. Now, just a comment, Kapitsa built the liquefier that was in Cambridge. He had gone back and forth. This is a story that's well known in low temperature physics, but probably not well known outside of it. Kapitsa had gone back and forth to Moscow. Okay, he had been a postdoc under Rutherford, and he was going to take over, I think, for Rutherford. And then he went back to Russia at one point, and Stalin said, "Nope, you're not going back." So Stalin helped.
Sounds familiar.
Yeah, right. Stalin helped. I'm sorry. So Kapitsa built up a lab in Moscow. He rebuilt the liquefier, probably made it better. But anyway, he had built both liquefiers that gave this data. All right, and the fact that the laminar flow is suppressed indicates a very large Reynolds number and turbulent flow. And here's one of the consequences of the low viscosity. A film of helium-2 rises up the inner surface and to the outside, forming drops, and then the beaker will empty. And here's an example. Okay, you don't have this happening in helium-1. Okay, an ordinary fluid. It's only in helium-2. The reason it rises is just surface tension. It wants to wet, but it can rise very high. I'm sure there's a limit to it, but to how high it can rise. But in this case, the limit is not very great. What am I talking about here? Okay. Anyway, Kapitsa wrote that helium-2 was in a special state which might be called a superfluid, and for that he got for that and other work he got the Nobel Prize. Notice much later. Okay, 41 years. Now, Allen and Misner, that was the guy who was the graduate student in Toronto. He was in Cambridge at this point. He noted that the flow did not depend on the pressure head or capillary diameter. And Balabar considers that this is the real breakthrough. They did not get the Nobel Prize, okay? By the way, I have looked at Kapitsa's collective works. He was a very impressive guy. And he could have been a mathematician in addition to doing experiments. So he designed extremely sophisticated experimental devices to measure all sorts of things. And I'm told that he did an awful lot of the engineering of transmissions that worked through the Russian winters in tank transmissions, okay? And then, at any rate, Allen and Jones also discovered the fountain effect in 38. And if you've got two regions of helium-2 connected by a capillary and you apply a heat current, it made the level rise on the warm side. And if you gave it a very large current, you would get a jet. There's an example. You shine in radiation on the left. You've got some powder. You've got your capillary, and you see a jet forming. That's obviously a schematic, not a real figure. Okay, now I'm going to get to some theory. All right. So first, Bose in 24 gave us statistical counting properties for light, and using it derived the Planck distribution. Photons are bosons with no mass. Remember, it was first, the Planck distribution was just found empirically by Planck, and then Einstein gave sort of a theory for it, but it was not until Bose talked about the statistics what the statistics should be for the system, that Einstein felt comfortable with it, and he studied the statistics of, therefore, non-interacting atomic bosons with mass and predicted what we now call Bose-Einstein condensation. And what that is that at high temperatures, Bose statistics works with chemical potential. I guess I should have had this on the top of my brain, but I don't. I think zero. Someone can help me. Who can help me here? Chemical potential 0, and then below it, at the transition, the chemical potential develops. Okay, a positive
Above.
value. Yeah. Okay, above. Okay, and then you're going to get stuff condensing into the zero momentum state. Now these are non-interacting particles. Okay, and that's important to keep in mind. Helium-4 is a boson, and we know that because it's got an even number of fermions. You've got 2 electrons, 2 protons, 2 neutrons, 6 fermions. That is a boson. Now Simon, in '36, realized that in this helium-4, the uncertainty energy is comparable to the weak van der Waals atomic interactions, and that meant it's a quantum system. Okay, so that was an early hint that became important. And then London in '38 actually applied the theory of Bose-Einstein condensation to helium-4. So he took the mass of the helium-4 atom in the theory that Einstein had developed, plugged in, found out the transition temperature was about 3 degrees, not far from the experimental value of around 2.2 degrees. Let's say that's good enough. And he found the specific heat near the transition was similar to what was observed. Not bad, okay. So what is the two-fluid superfluid theory? Well, Tisa, like London, was running from the Nazis. And he was visiting London in Paris. This is a strange sentence. How can you visit London when you're in Paris? Well, Fritz London was living in Paris. So, I think, what the name? I've forgotten the name of the lab, but it was the one that the Gen later was at, so Tisa developed a two-fluid model based on Bose-Einstein condensation. And the idea is that the condensed atoms give 2 phases. There's the normal fluid, which is the non-condensed atoms with a velocity v sub m, and the superfluid, which is the condensed atoms, those in the zero momentum state. And it has the superfluid velocity v sub s. So, and he predicted a new temperature mode. He explained the decrease of the viscosity, he explained the fountain effect, but Landau showed that Tisa's theory was not consistent with superfluidity. Landau gave a more consistent two-fluid model. Okay, it really has a solid physical basis. The superfluid is closely related to the ground state with no entropy, no viscosity. The normal fluid is a gas of Bose excitations. It has entropy and viscosity. This might be the first place that the idea of an elementary excitation of a many-body system appears. This is a really remarkable paper that Landau wrote. He used the idea later. He developed the idea of elementary excitations in Fermi systems. And I've been leaning on these theories of Landau throughout much of my career. Anyway, he showed that the excitations must be stable. They're kinematically unable to decay, and thus it's consistent with superfluidity. He got the Nobel Prize in '62, and I'll show you how they're consistent. It's a very simple argument, okay? He predicted the specific heat value, what it was like. He predicted a temperature wave called second sound. He got the second sound velocity in quantitative agreement with the experiment. But I have to say this, that he really didn't have the idea that well, let's see if I'm going to show this in the next one. Yeah, he didn't have the idea that temperature dominates density in second sound. So when he published his work, people didn't know that you used a heater to produce it and a thermometer to detect it. So his former student Lifshitz, now there were two of them who were brothers. Now, the brother who you see on all the Landau-Lifshitz papers is EM.
He's the note taker.
What?
He is the note taker.
He's a very bright guy.
Okay.
Okay, you read his stuff, very, very bright guy. Okay, no question about it. You know, what the Russian phrase, not a word, not a word of Landau, not an idea of Lifshitz. I don't believe that. You read some of these very carefully crafted sentences in, for example, their book on electrodynamics, classical electrodynamics, and with very few but very accurate words, Lifshitz tells you what goes into a derivation, okay? And he's on the money,
But
okay?
doesn't show it. He doesn't show it.
And not necessarily show, okay? You cannot do the same with say, Jackson.
Okay.
Jackson, it's like, what's going on here? What's going on here? Okay? That's been my experience. So I want to defend EM.
What does
Lifshitz
this
from that.
phrase, temperature dominant density, means what?
In other words, the relative amplitude, if
Okay.
you know, okay, in
Okay.
whatever, in degrees versus, you know, mass per blah blah blah, okay, is in ordinary sound, which is called first sound, is low, but it's much larger in second sound. So you've got to use a heater to produce it, a thermometer to detect it, and that was done in '47 by Peshkov in I guess in Moscow. So let me talk about Landau's two-fluid superfluid theory. He argued that for a many-body system with fluid symmetry, the deviations from equilibrium are excitations of definite momentum. It's got translational symmetry, okay? And he showed that Tisza's non-interacting bosons are unstable. You can have the states decay to one another or to the wall. And the argument was kind of like this. Let's make believe you've got the capillary at rest, okay? On the capillary, and you've got the fluid flowing rightward like that. The excitations are defined relative to the fluid, okay? So let's consider the possible spontaneous creation of an excitation with momentum P and some energy E sub P, all right? And see if we can decrease the flow, all right? So if P is leftward, you're slowing it down. You can show that there's a change in center of mass flow, energy, okay? The kinetic energy, it's down by minus PV. So if the net energy E for the excitation, E sub P minus the PV as viewed in the capillary frame is less than zero, which means if the velocity is big enough, okay, then you can spontaneously create excitations and destroy superflow. It's a very simple argument. Now this sounds like purely classical, but it's not really, because people use this idea when they calculate, when you have sort of sliding of two materials against one another, you will make up the extra energy by attributing it to either the substrate or some other excitation in the fluid, and then that way you can get a friction coefficient. Okay, so and you'd use Fermi's golden rule to do that. I've done that. Okay, so just be aware that it sounds like a purely classical idea, but I mean, Fermi's golden rule uses energy conservation, and this says you're going to be able to give up some energy somewhere. So the process is this, you know, the flow it'll slow down. Now Landau, to fit the specific heat, at low temperatures, like below maybe 0.8 degrees Kelvin, okay, he took the sound wave excitations as his excitations. He took a linear a dispersion relation, where c is the speed of sound, not the speed of light, okay? And at higher temperature, he first, and when I say first, in 1941. Later, he took a different hypothesis, okay? He first assumed a second mode, with a gap, okay? So it would only turn on when the temperature got to be hot enough, okay? And then he assumed it was p squared over 2m. It was called a roton, okay? And it's a misnomer because it makes you think that something's spinning. Forget about it, not, okay? And he treated both excitations with Bose statistics. And then he gave a theory for the normal fluid fraction as a function of temperature. I could do that, but come on, let's not deal with that. As a function of temperature, and he used Bose excitation properties. In other words, thermal weighting, as if they're bosons. And the superfluid component, he showed is closely related to the ground state and has no entropy or viscosity. And he developed a macroscopic dynamical theory for the two velocities, Vn and Vs. And the macroscopic variables that they use are given in this energy density. So if we look at the energy density, like this, in this case, I'm using E as an energy density before I used it as an energy. Here it's temperature times ds as the entropy density, chemical potential mu, d rho, mass density overall, and then here are two terms associated with the kinetic energy of the system as a whole, normal fluid times the change in the total current density, which is due to the mass flow associated with the normal fluid, rho n times Vn, and the superfluid, rho s Vs, and an extra term, J sub s times dVs, okay, where Js, the superfluid mass flow, is rho s times the superfluid velocity relative to the normal fluid velocity. That's just the way it works out here. One equation I did not write down, I probably should have, but I didn't, is that when I said the superfluid is closely related to the ground state, you can imagine that you've got a system that it has some energy function. In this case, the energy function is replaced by the chemical potential, per unit mass. And the velocity, you'd say, well, it might go, if it's a classical particle, along the negative gradient of the energy, something like that. And in fact, the velocity, or not the velocity, the acceleration is along the negative gradient of the energy. In this case, the velocity, the acceleration of the superfluid velocity is equal to lowest order, neglecting other stuff, the negative gradient of the chemical potential. Okay, so now Bogoliubov went on to show that this idea of stable excitations worked for helium, all right? And Landau, I don't know the order now. It's an interesting question because Bogoliubov, I believe, did his work in 47. Landau did this work in 47. Landau was motivated to give a better fit to the specific heat data. He took a different model for the energy spectrum of excitations. At low, and with this a single complicated mode instead of two, okay, he fit the specific heat data. And this is what he did. He still had phonons at low momentum, but at intermediate momenta near some P0 called the roton minimum, you had a gap, but the gap was around some value P0. And Bogoliubov, around the same time, found a single mode of stable Bose excitations in a model for weakly interacting helium-4. I'll show you what it sort of looked like, but just note that in 56, Feynman gave a more microscopic theory with a backflow picture for roton minimum. And then about that time at Brookhaven, measurements were made which supported that. And here's more recent data from neutron scattering. And so that's a picture of what the mode spectrum looks like. And this spectrum is consistent with both phonons and rotons. Okay, and the rotons would be made more readily according to the Landau criterion for the energy over the momentum. It would be something like 6 over 2 or 3 in the appropriate units for the velocity, flow velocity. And here it's got a higher slope than that. All right, so just keep that in mind. So according to Feynman, this is what everything, that's what will cause decay of the superfluid if it flows too quickly. And I'll bring this up later because it turns out life is more complicated than that. And the flow, it loses the superflow property at lower velocities due to another effect, which Feynman also had his hand in. It's consistent with Landau's requirement of stable excitations. And just as a comment for later, okay, for Bose atomic gases, you can have these Bogle-U bonds, and they give a stable Bose-Einstein condensation into the ground state. Oh no, it all got messed up. I've had trouble getting everything to come in at the right time. But let's go with the first thing. Just so you know, superfluidity was discovered in the 70s. I mentioned that. And they find it in the millikelvin range, and it very much depends upon pressure. Here's a picture, all right? And you used to have, who remembers Richard Webb? Okay. Right, he was here, exactly. He worked on this stuff with his advisor, Wheatley, who co-discovered, okay, the superfluidity, okay. Actually, I am told that Wheatley and maybe Rich at the same time got the data first, but they were plotting it up point by point. I don't know, did Rich ever tell you this story? I've heard this many times from the Cornell people, but they at Cornell had a graduate student who automated everything. So as soon as they took the data, the plot points were plotted on a chart recorder. And poof, something happened. So at 2 in the morning, Ashraf, the graduate student, called Richardson and told him, we've got something happening here. And so the Cornell group, which was 3 people, got the Nobel Prize for that. But anyway, this is what it looks like, and there are 2 superfluid phases depending upon what the pressure is and what the temperature is. And so now the modern theory is basically due to, like, he found microscopic order from the nuclear magnetic resonance shifts. This is a remarkable paper when he first realized this. He argued on extremely general terms that there had to be some sort of symmetry breaking. I read that paper and it's like, whoa. And Phil Anderson, I think, read it too and did whoa too, because at one point I heard from Anderson, yeah, I think he said it at a conference in 75, I think. Maybe it was in 73, I don't remember. He'd not met Leggett yet. He made the comment, he's a very smart guy. And yes, I mean, very smart guy. At any rate,
And Leggett also got Nobel Prize.
Also got the Nobel Prize for this work, basically for this
yeah.
work, yes. Okay, and just a comment for the macroscopic dynamics, you can use Landau's theory, but again, I mentioned it, you make the certain properties anisotropic. Okay, so now we're segueing to something new, okay? The something new is, okay, we know about superfluids, there are 2 velocities, okay? And just a comment, the superfluid is driven by the negative gradient of the chemical potential per unit mass, that's fine. What drives the normal fluid? Well, the rate of change of the momentum density is driven by the gradient of the stress tensor. So that's a second equation of motion. So if you know how the momentum density changes, and you know how the superfluid density changes, you take sort of the difference, and you can figure out how the normal fluid responds. And it turns out it responds to both pressure and temperature gradients. But we don't have to go into that particular detail. It also is subject to viscosity, and we don't want to deal with that. And anyway, let's talk about the early supersolid proposals in theory. Andreev and Lifshitz gave a defect-based two-fluid theory for the macroscopic dynamics of superfluid solids. And they had 2 Galilean velocities. The word should have been switched, normal and super, okay? And the mass densities rho n and rho s. There was a lattice coordinate associated with stress and strain, but it carried no mass, okay? There's no 3 velocities. Now, they didn't, they had certain limitations to the theory. I don't think it really applies, but many ideas are correct.
Would you please tell us what superfluid is? Supersolid?
I can't tell you until I tell you.
Okay.
So, right, you're saying now to say, tell us before I've told you.
Okay, all right.
Okay.
I gotta follow what this means. Okay, no problem.
Right. No, it will come.
All
It
right.
will come. There's the third velocity is associated with the lattice, and I will tell you the equation of motion for that. And I won't derive it. I'll say what it is and what it responds to, and I hope that will answer your question. But right now, I want to tell you what had been done, because the theory had nearly the same structure as Landau's macroscopic theory, but it included elasticity, and they generalized some work to include defects. It turns out that's really quite important. I've got to push on that a bit more in my own work on the superfluid.
Defect in the lattice?
The lattice, yes. There's a lattice. Okay. In other words, they made solid helium-4. That's well known to exist at higher pressures. Okay. And the thought was that maybe this could be superfluid but solid somehow. How? They didn't really know. They suggested that the defects did it. I don't think so. All right. Leggett independently gave a phase gradient-based theory of superflow of a solid at 0 temperature. Okay, he called it non-classical rotational inertia. Okay, so the idea would be, he said, well, you do this experiment where you rotate maybe an annulus, okay, and you'll find that you don't get the classical moment of inertia. You're going to get less. And he said the way we do it to find the superfluid velocity is the wave function, the many-body wave function, right, 10 to the 23rd particles, has a common phase associated with it. All right? I mean, every particle, it's bosons, they all have that same phase as a function, of position. And he took as the superfluid velocity h bar over m, the gradient of the phase. Okay? And so, in this case, Vs is defined relative to the lattice, so it's not a Galilean velocity. Okay? Now, Andreev and Lifshitz took their Vs to be a Galilean velocity. And I'll talk about this again. So here's a picture of what you can have. You just rotate an annulus, okay? And just a comment, so this doesn't sound like magic. What is Leggett talking about? The man's crazy. We live with it all the time. Just about every atom with more than 5 electrons has got this sort of thing happening. Okay, boron is the first one that's got it because it's got the following. Okay. I didn't go through it, so I've got to go through counting. Okay, two 1s electrons, no phase gradient because they're s electrons. Two s electrons, no phase gradient because they're in the s state. 1 2p electron, that has a dependence e to the I phi on the azimuthal coordinate. That's the thing we're talking about there. Okay, and so you've got momentum, So really, it'll be angular momentum, but it's still a momentum. There's motion inside that boron, and it's done with a constant density. This is really important. So you can ask yourself, go back to Leggett. How can you have flow without the stuff actually moving? The lattice is fixed in Leggett's picture. Well, the lattice, there's only a lattice of 1 in boron. There's only a lattice of 1 in every atom in this thing. But there's still going to be some angular momentum flow. You might have no net angular momentum flow, but there's still, if you look at a given electron, there's going to be angular momentum flow without changing the density. All right? So we're already accepting that idea. Okay? So at any rate, Leggett found a non-classical rotational inertia, which is effectively the same thing as the superfluid fraction, F sub s given by rho s over rho. It's less than 1. He didn't give any dynamics. He just said, this should happen. Okay? And basically, the idea is, let's say you have a one-dimensional situation, that if you've got a mass, this is zero density background. If you've got a mass density that's sort of like that, okay, the way the system is going to flow, I guess I'll give the equations on the next page, but let me just indicate it to you. You have around this, you go around this guy, there's a fixed sum total phase gradient associated with the rotation, okay? And when you're in a rotational frame, when you go around 2 pi, if you're in a rotating frame, the phase difference is not 0. It's proportional to something. It's proportional to the rotation frequency. The current is going to satisfy something like a continuity equation. d rho dt plus div j is 0. Okay, J would be the atomic density, which I was indicating is something like this. Okay, and the V is your velocity over there. There's the J, and you now want to have d rho dt in the rotating frame to be 0. Okay, which is like boron. Okay, no motion of the mass, but the J is non-zero, but it's got 0 divergence. Well, how do you do that? Well, in the regions where the density is high, you've got to have low velocity. In the regions where the density is low, you've got to have high velocity. That means that the total velocity change is going to be much bigger in the low mass regions, and that way you can build up a significant amount for the change in phase, if you like. Okay, if you integrate Vs times dr, which will give you your phase difference basically, then it's going to give you lower momentum than you would expect, average momentum, and therefore you're going to get a superfluid fraction that's less than 1. All right, so Fernandez and Puma in 74 and in 76, we studied superfluid fractions quantitatively for models of atomic scale lattice density. We treated that density as a sum of Gaussians of some range B on a simple cubic lattice of unit length A. I'm just repeating myself now. In the absence of any many-body correlations, the supercurrent satisfies the continuity equation. That's why, remember, d rho dt is 0 in this steady state situation. No mass, the mass isn't flowing, but you get momentum, okay? The divergence is 0, and the momentum density is blah, blah, blah. And so you can then find what the structure is, what the supervelocity is if all the way around if you impose a net change around that annulus, okay? And then you can compute the total energy. So let me just comment on what that involves. The ordinary kinetic energy, rho, local atomic density variations. The local Vs involving local phase gradients, not the V average, that's the delta phi imposed when going around, but though in the previous diagram, and you say, okay, that's equal to the average rho s over 2 times, this should have a factor of h bar over 2m, because it's supposed to be the average superfluid velocity, and you square that. And that'll give you the superfluid fraction. And the more extended you've got it, the larger b over a. In other words, instead of, if you've got something that's shaped like this, if you have the atoms more extended, it's going to be big and then stay big. Okay, it'll stay at a finite value mostly, because the Gaussians will overlap. It'll look more like a fluid. Okay, if it's really big, it looks just like a fluid. Of course, you should get superfluid fraction that's 1 in that case. And so this is what you get for larger b over a. Small b, localized, it drops to 0 very quickly. Okay, and I argued then that something like an Andreev and Lifshitz dynamical theory works for Leggett's phase flow superfluidity, which is not Galilean. If you say, just by fiat, the rule is you give Vs a Galilean part, okay? And I gave a new dynamical theory with nonlinear terms. It looked different than Andreev and Lifshitz, but it was equivalent to it. I couldn't understand what Andreev and Lifshitz had done. It was just not enough details. I couldn't figure it out, so I had to do it my own way. Anyway, the dynamical variables in the energy are what was in the previous work of Landau with a new term: stress lambda and strain dw ik. And the other stuff is the same as in Landau. Okay.
And this is coming from the lattice.
Say that again?
This is coming from the lattice.
Yes, this is exactly coming from the lattice. Okay, and they did a lot of significant work on elasticity theory at this point, which I don't want to get into. It's sort of technical, but normally one would say, well, let's not worry about how that lattice will depend upon the entropy density, how those constants in the lambda ik will depend upon the entropy density or upon the chemical potential. But in fact, there are dependencies like that, and correspondingly, the temperature and the chemical potential will depend upon the strain. Okay, then they're related by a Maxwell relation, and under certain circumstances, the theory will reduce to the simple elasticity that's in Landau-Lifshitz elasticity. But if there are defects, the game changes. You don't get the same stuff as in Landau's and Lifshitz elasticity theory. Okay, so now people decide, let's take a look. Okay, can we find some soiled? No, it's not soiled. It's solid helium-4. Anyway, in 2004, Kim and Chen, they're at Penn State. Kim is back in Korea, right? As a graduate student, he came to work for Moses Chan. They thought they observed non-classical rotational inertia in solid helium-4, which I remind you it's under pressure. It's not really high pressure, but it's certainly multiple times the atmospheric pressure. And so I figured, okay, let me think about this theory again. And I realized at that point that there was a missing mass density. As I'm just repeating this now, at 0 temperature, the superfluid fraction is 0, and also at 0 temperature, the normal fraction has to be 0.
Fluid is 0 at 0 temperature?
Normal fluid.
No, superfluid, you said.
The superfluid is less than 1.
Okay.
Less than, not the whole thing. But the normal fluid is literally zip,
Okay.
0, nada. Okay, zilch. Okay, so I suggested there has to be some additional momentum-bearing velocity associated with the lattice, but I didn't develop the dynamical theory. Okay, and that's in part because the experimental motivation disappeared. Kim and Chan retracted their claim of having observed true non-classical rotational inertia. They reinterpreted their large flow under rotation as flow along dislocation lines, of flow of the helium-4 along dislocation lines. So that seemed to be the end of that. There were no relevant experiments for nearly 20 more years. And then Bose-Einstein
What's a
condensation.
dislocation line?
I'm sorry?
A dislocation line? Have you told us what a dislocation line
Oh,
is?
dislocation lines are, okay, I assume, okay, every real material is not perfect, doesn't have a perfect lattice. And you can have point defects, but you can also have line defects. And simple ones are called, there's screw dislocations and other kinds of dislocations. And it means that lattices don't fit. So you might have coming into some region, here's an artificial plane. You might have let's say you've got 5 layers coming in here, and you might have 4 layers there. You can't match it. So it tries to make a fit. And there's a line like this along which you say there's a dislocation. Okay? And so their interpretation, to be honest, I don't really have a good, even though I'm condensed matter, I don't have a good way to describe dislocation lines. I've not been happy with any discussions I've seen. It's the kind of thing that I think was developed very quickly, and then the people in the area said, oh yeah, that's the way it works, and it was rarely explained cleanly. Okay? Is there someone here who's a condensed matter person who can cleanly explain dislocation lines?
This is your talk, but one can first draw a lattice with just 1 point removed, then remove 10 points in a line. Then you start getting a dislocation line.
Yes, and it would end up with something like 5 rows, planes
Yeah.
coming in, or 4.
Missing atoms along a
Yeah,
line.
yeah, okay. Thank you.
It seems to me that in the rotational geometry, the cylindrical geometry in which they're looking for the non-classical
Rotational inertia.
rotational inertia, that you can't maintain the same lattice constant across the radius without having dislocation lines.
The lattice can't be perfect.
Yeah,
Yeah, I agree.
that's
I-
true.
Okay. Yeah, yes, you can't have, the translational symmetry, true translational symmetry. Right. I guess they assumed that when they machined it, started out with the right symmetry, and then when they machined it, at least for the interior, it was okay. I don't know. Now that's a real serious detail. But anyway, let's get to Bose-Einstein condensation. There were early attempts in 1979, to observe Bose-Einstein condensation in spin-aligned atomic helium. If you just have atomic hydrogen. If you just have hydrogen gas, you'll form molecules. But if you put on a large enough magnetic field, you can spin align them, and they will not form molecules. Okay, and so this was later observed in '98, but that they were not the first. Okay, and to get to this stage, you first needed laser cooling, which is a Nobel Prize for a few people. One of them, Steve Chu. Now he was at Bell, now at Stanford, and I've forgotten the names of the other guys. Here's a picture I'm going to show you now of what one of these labs looks like. So I'm going to show you the Ketterle lab. The Ketterle lab was one of the labs that observed Bose-Einstein condensation, okay, in a different system. And you can see Ketterle on the left. There's a whole mess of stuff in there, and there are bunches of lasers. They needed to get Bose-Einstein condensation, not just cooling. You had to cool it below the Bose-Einstein condensation temperature. So here's an example of what the laser table looks like for a successful operation. Okay, it's more complicated than in this case. I guess they both look like messes, but anyway, it's just incredible. And the figures above show that to study Bose-Einstein condensation, at least with atoms, you need what has been called a laser factory. Okay, You need lasers to cool the atoms. You need lasers to confine the atoms. You need a laser and maybe multiple lasers to probe the atoms. And you need lasers to measure the atoms. I mean, this is lasers here, lasers there, lasers everywhere. Just horrible. I mean, it's really amazing that they don't go blind. You also need a magnetic field to tune the atom-atom interaction due to distant nuclei interacting by what's called the Feshbach resonance. I don't want to go into that, but there are nuclear processes that very much depend upon subtle occupations associated with the magnetic field, and that will determine how distant nuclei interact, which is like, what? How's that possible? But it does. It does matter. So anyway, in '95, Cornell and Wyman at Colorado studied rubidium-87. And I just want to go through the count here so you know, you can agree with me. Yes, this is a boson, okay? It's got 41 electrons, 41 protons, and 46 neutrons. Total number of fermions, even. This is a boson. Also, Ketterle at MIT, whose picture is above, he studied sodium-23. Sodium, 11 electrons, 11 protons, that's an even number, and 12 neutrons. Again, an even number of fermions, okay? They, in '95, they independently discovered Bose-Einstein condensation in atomic gases with Bose symmetry. They got the Nobel Prize for that in 2002. Hewlett in '95 got results on lithium-7, but he just had too few atoms to give really good data. All right. At any rate, Cornell and Wyman in '99 observed quantum vortices, which is a signal of superfluidity. This idea of quantum vortices is due to Onsager and Feynman independently. Now you're going to say, if Onsager had the idea first, why did Feynman get credit? It was a conference statement that an idea that he gave at a conference question. What's that? It was not a published article. People sort of remembered it. It might appear as a question, but not much. He had thought about the issue, of course.
Did Feynman hear it?
I don't think so.
Okay.
In 1949, Feynman, I think, was doing quantum field theory. I don't think he started to think about helium until '54. Okay. Anyway, so let's go on.
Okay.
Yes. Time to go?
Yeah.
Give me, okay.
5 minutes?
Yeah, hopefully less than that, okay? Anyway, what happened is the group in Ferlano, okay? Francesca Ferlano in Innsbruck worked with, just a couple of years ago, with dysprosium-164, created an optical trap with tens of thousands of atoms at 20 nanokelvin, okay? And these things have dipoles, and because of that, you can have a magnetic field at an angle like this, and then rotate the magnetic field effectively like that, so you can stir the system, magnetostirring, okay? And they observed extra dots in the diffraction pattern, and it indicates superfluid behavior. And here's I think I lost some information. Here's some pictures that indicate that vortices are forming, okay? And these are just different examples. I don't want to go into these. But they did theory. They did some theory. They found that for a certain localization parameter, I won't go into the details of the model, but they found that they would expect a superfluid phase to have a superfluid fraction that was below 0.5. I'm sorry, that should have read above 0.5, which is rather large. So here's a picture, and the point here is that in this region, okay, you could have a rather large superfluid fraction lower there. At any rate, So they got that. And now, I think these two slides got mixed up. But here's some data showing what looks like vortices. This is experiment. I showed you some theory. Here's experiment. And you can see what looks like vortices forming in the system. And it gave me motivation to develop the three-velocity theory. So here's the results, okay? The big picture is I used Onsager's irreversible thermodynamics. So I used thermodynamic variables A, so you write down the energy density, blah, blah, blah. It's really just like what was in the earlier theory, but I had to add an extra term. And where's the extra term? Do I show it? There's an extra term that involves, well, I guess I didn't show it, but it doesn't matter. But there's an extra velocity, okay? So that you've got your current density is not just normal velocity stuff, but and superfluid velocity, but you've got your velocity of the lattice. And here that rho is the same as the rho that I used previously. And let's see what we have here. Here's the thermodynamics, and the difference is in this new term. Okay, I probably should have just gone to this immediately, but I didn't realize I was going over. At any rate, here's the, okay, punchline is right here. You've got this new velocity. What does the superfluid velocity, the normal fluid velocity respond to? It responds to the gradient of the chemical potential exactly in the same as with the superfluid velocity. That indicates that this Vs of L indicates that Vs and Vl are somehow associated with the ground state in a quantum mechanical sense. They're linked together. But in addition, that VL responds to the lattice elasticity. And this is a misprint. It says neither VL, no, it should say neither Vs, the superfluid, nor the normal fluid responds to the lattice elasticity. VL, therefore, responds to the chemical potential as if it's part of a ground state, and it responds to the lattice elasticity, which you would expect. But then there's something else, which is the only thing I anticipated, that the normal fluid sees the solid as a net. And if you have a fluid going through the net, there's going to be drag, and there's a drag term. At low velocities, they move together, and at higher velocities, you might expect 3 modes at high frequency. But I found that for a perfect lattice, one of those mode velocities is 0. And let's just say it needs further study, blah, blah, blah. But the big picture is right there. This new velocity responds, and I love this, that it responds the way the superfluid does to the chemical potential gradient. So it says it's sort of in the ground state, but it also says it also sees the lattice elasticity. And lastly, when there's normal fluid, not at 0 temperature, at finite temperature, it causes drag on the normal fluid, and of course vice versa. And it's a nice, to me, nice clean physical picture for someone who already knew about superfluids, who already knew about lattice elasticity, and was used to dragging a spoon through his coffee. All right? And it's got all those features, and I think let me just leave you with that. Oh, it doesn't matter. Summary. No more summary. Go away. Thank you for your attention.
Okay, so we'll have private questions, but otherwise,
I'm sorry I went over. I didn't realize. I was having too much fun. Thank you. You've been a very, very good audience.